Okay, now let's look at the horizontal stretches, compressions, and flip across the vertical axis. So this is something similar to doing it vertically, but not horizontally. But just like we just saw with the horizontal shift, things are going to look a little backwards here. So consider the function f of x and what occurs when we consider the function g of x, such that it is written in terms of f. What we're doing is multiplying the variable, and that's my variable, x, um, where a is a constant, such that a could be greater than 1, a is between 0 and 1, a is less than -1, a is between -1 and 0, and a is -1. Okay? So given the graph below, f of x, graph f of negative x. So we're going to start with the following, this one. What would happen if a is equal to -1? In other words, when I write that, I could have easily written that as -1 times x. So these are saying two different things. This is the opposite of x, -1 times x, but the result is the same. So just like before, all I'm going to do is write down these ordered pairs. And now, what is it that I'm doing? Notice I'm not affecting the y at all. So I'm going to write the y over again. But what am I doing to the x? Well, it looks like I'm not adding, subtracting anything. What I'm doing is entering something in and taking the opposite of it. So unlike horizontal, this one's a little easier to comprehend, but notice that the idea still works the way I explained it. What -5 produces a 3. What would you need to enter to make this a -5? The answer is +5. But another way of looking about it is if I enter a -5, what do I get? I get a 5. But anyway, if I enter a 0, what do I get? 0. If I enter a 2, I get -2. But another way, again, thinking about it is if I want to get this 2 output, what is it that I need to enter? I need to enter a -2. So the opposite of -2 is 2. Okay. So, and what I write down here is what I entered to get that value. That used to be the correct value. So what happens when I do that? Well, let's graph and find out. 5 goes to, or -5, 3 goes to +5, 3. So in fact, notice this, it moves across the horizontal, meaning the y hasn't changed. 0, 5, well, because it's right on the vertical axis, it stays exactly the same. And finally, 2, 0 becomes -2, 0. So it looks like the graph has flipped by joining these points. Looks like I created a mirror image across this vertical axis. And so the result of x has been flipped across x-axis. No, against y-axis, vertical. So given the function f of x, the function f of -x, or f of -1 times x, is the graph of x, but again, flipped across vertical axis. or y-axis. Think of it as creating a mirror image for the graph across the, again, y-axis or vertical axis. Again, there's nothing magical about calling vertical y, but it's by convention. And that's all we've done. Okay, so that's care of this. Again, it looks like, again, multiplying by a -1 has caused a flip across one of the axes. Remember, when we multiply the entire function by -1, it flipped across this axis. Okay. Let's come over here and continue. Graph f of x equals absolute value of 0.5x. All right, so let's just continue with this thought pattern. Looks like the original function, or the basic function, is just going to be the absolute value of x. So let's kind of do a couple of mind things here. -2, the absolute value of -2 is a +2. -1 is 1, 0 is 0. +1 is 1, +2 is 2. Okay, that's the original function. What happens if now what I'm saying is enter 0.5, multiply before you take the absolute value, multiply by 0.5. So again, from experience now, we know that when I do this, so write the equation down. This is not going to change. The output is going to stay the same for now. That's what we're going to think about it. But notice now I'm going to write just 0.5x. Okay. The function is the absolute value of 0.5x. But what causes now, what's the result of this? Of multiplying my input variable by 0.5 before I take the absolute value. And now again, we've seen that with the horizontal, the y's are not changing. It's what's changing is the x. So before, -2 gave me 2. But again, a way to think about this is that imagine this actually just stayed the same. All I'm doing is entering it, pairing with a different value to get that 2, because I need it because of this 0.5. So what if I'm going to multiply this input by 0.5? What do I need to enter to get that -2 back out? And for this particular example, if I enter -4, -4 times a half gives me -2. So again, the input is -4. That will produce the -2, which in turn gives me the 2. Again, it seems, I know it's strange, and you have to it's almost like a shell game where you're trying to follow the whatever it is under the cups. I've seen those people do the cups thing. That's what's happening here. That's why it is mentally confusing, but let's just check it out. I'm not going to move out of here. We'll check this out. If I would have over here, notice, enter, I said I enter -4, right? And think about what I just said, what's about to happen. Half of -4 is -2. F of -2 is what? Oh, sorry, half. No, absolute value of -2 is a 2. So again, notice what's happening. There it is. 2 -2 gives me 2. So you can think of this as there's something happening before I go back to the original graph. And of course, the reason it shifts or it does some kind of transformation is because what I'm pairing up is not this output of this function, which I'm composing the original with. What I'm pairing with is the actual input. Then it transforms inside of it, and then it gets me. So this is the pairing now. But when I pair again and I graph it, well, all of a sudden I get a brand new picture. So what is, for example, what used to be a -2, 2 now is at -4, 2. So right there. And if I keep going in this direction, -1 is what I want to eventually pop out of here to get a 1 back out. But what is it that I need to enter here to get a -1, looks like a -2. So now -2, half of -2 is -1, -1, absolute value of -1, 1. So -2 produces a 1. 0 still produces a 0, right? 0, half of 0 is 0. That's the value here of 1. But then, of course, this is completely symmetric. So what happens here? 1, well, if I enter a +2, then all of a sudden I get half of 2 is a 1, 1 is 1, and again, 4 over here. So if I were to graph the rest of these points, what I get is this. So the original, again, 0, 0, 1 is 1, and 2 and 2. There's the original one. But it looks like what I've done is stretched it horizontally. These points have been stretched. By how much? By a factor of 2. So this point has been moved this point 2 has been multiplied by 2 to get the 4. This one was a 1, got multiplied by 2 to get this right here. So even though I'm multiplying by a half, it looks like what I'm doing is really all the x values have been doubled. Leave the y value alone, but we have doubled all these values right here if you take a look at it. Okay? We'll come back to this in a second. Consider the graph of f of x equals x squared. Again, it's a parabola. Graph 4, f of 4x. Okay? So if I come over here, it's easier to see with these graphs where the origin is sitting right here than it is with other things. So keep that in mind. -2 is +4. -1 is 1. 0 is 0. 1 is 1. And 2 is 4. So again, what am I doing? I'm graphing this right here, right now. This is f of x, the original. So what is it I want now to do? I'm not graphing, I'm creating a table for that. Well, it looks like what I'm going to do is multiply my input by 4. And then what I want to know is, okay, so what is f of this result? Again, from experiments, I know that this is not changing. And again, why is it not changing? This is not an full explanation, but at least intuitively, I'm affecting the input. Then the function does something and produces the output. So the output is staying exactly the same. What is changing, because I'm doing something before the function gets a hold of it, I'm affecting when that output happens. So in my mind, when I look at these type of compositions, I think of more like, I don't know, like time travel or something. The output is still the same, but where it occurs is now being changed. When it's happening, is completely different because I am multiplying by 4. In other words, before it used to happen at -2, right? But now by multiplying by 4, if I think of this as time, all of a sudden, the multiplying by 4, it's happening 4 times faster than before. And again, you would think, like, oh, it's -2 times 4 is -8, should go there. No. Because what I want is still the same output of 4. Here's another way of thinking about it. If, like, I don't know, some input to get 4, -4, -2 got me the 4. But now because I'm like some kind of maybe a car that got souped up. Now I'm souping this thing up, and as soon as I put the input, it's immediately going to get souped up by a multiple of 4. So all of a sudden, I just don't need as much input to get the same output. So what is it I need here to get -2? Half of, really a quarter of that amount. So half times 4 gives me 2, -2. In fact, I'm going to make sure I get this right. It's -0.5. -0.5 multiplied by 4, I get -2, and that provides me with the 4. So now we're getting to the point where let's talk about this some more. What's an easier way of doing this? Everything is backwards. So when we did the shifting horizontally, you notice I had to go, if I'm saying +3, all of a sudden I need to go to the left. If I'm just saying what appears to be bar to subtract 5, then I go to the right. How is this different? Another way of looking about it is whatever this number is, look at the reciprocal. And now multiply these numbers by the reciprocal. So what's the reciprocal of a half? The answer is 2. So now to go from here to here, all I need to do is go -2 times 2, -4. -1 times 2, -2. 0 times 2, 0. 1 times 2, 2. But of course, now that you see this, that's just a procedure, but it doesn't quite explain what is happening here. Well, would I need to do that? But that's, again, what's happening. So now here, the reciprocal of 4 is 1/4. So all I need to do is multiply everything by 1/4. So why am I doing it here, not now? This is I know this is a little harder for people to understand because, I'm creating these fractions. So what is it that I need to enter here to get a 1? The answer would be a quarter, or 0.25, a -1, so -0.25. Again, 0 produces 0, not a big deal. And then this is positive 0.25. So in other words, just enter 0.25, quadruple it, and I get my 1. Enter 0.5, quadruple that, and all of a sudden that gives me 2. So when I look at this graph, what is the result of it? The original one's right here. At -2, it produced a 4. At 0 and -1, it produced a 1. At 0 produces a 0. 1 produces a 1, and 2 produces a 4. So this is the original one. That's f of x. It's a parabola. I'm just kind of, we did this so this part is super exaggerated. Almost like, God. Okay, did not do a good job there. But now what's happening is the 4 output, which happened right here, is now happening much earlier at -0.5. The 1 output, which used to happen at -1, is happening again 4 times faster, so now it's at a quarter. Right here. And 0 is happening at 0. So there's a new picture of this parabola. Okay, I didn't do a good job trying to connect these points. Okay, I'm doing a terrible job. Did I tell you I was super tired? Right. And it's compressing. So it looks like my graph has compressed. Or my function compressed horizontally by a factor of, well, what's it a factor of? Again, factor means multiplying, so a factor of 1/4. So take all your old outputs, no, sorry, all your old inputs, multiply them by a quarter. Leave the outputs, corresponding outputs alone, and that's what's happening. So you're compressing horizontally. So again, because I'm affecting the x, so notice nothing, the y's are remaining on the same horizontal plane. It's just that everything is getting crushed. So the, again, this is no longer rigid. I'm compressing everything by a half. That's what's happening here. And when I did it over here, notice when I multiply it by half, what's happening? I am now expanding. So this one here was the original. Meaning absolute value of x, and this one is the transformed one. Right, so this one has stretched. By, and stretched horizontally by a factor of, in this case, 2. Theorem is just this. Given the function f of x, the function a of x, again, between where a is between 0 and 1, is the graph of x. But again, because this number, again, notice is smaller than 1 and positive. Well, yeah, positive. But what's happening? It's going to be stretched. When this thing that I'm multiplying is smaller, or between 0 and 1, is going to be but stretched horizontally by a factor of, again, if whatever a is, it's 1 over a. But again, factor means to multiply, just again as a reminder. If a is greater than 1, then the graph of x is of f of a of x, again, notice greater than 1, but it is compressed horizontally. By a factor of, and again, just 1 over a. Again, always take the reciprocal here. Okay, so for example, consider the function sine of x equals y. Write the function that is a horizontal stretch of sine of x by a factor of 10. So I want to stretch this. So whatever this looks like, I want to stretch it way out there. Okay, just go like that and just pull on it by a factor of 10. So, okay, so if I want to do that, let me just call this new function h of x. And again, I want to stretch it, so, and by a factor of 10, I want to do that. So I gotta do this. Okay. Is that gonna work? We'll check in a second. Here's g of x. It's a transformation of the function f of x, but horizontally stretched by a factor of 5. Okay, vertically shift down 3 units, write g of x in terms of f of x. Okay. So g of x, transformation of the function f of x. So this is my original. But horizontally stretched by, okay, I want to stretch this by a factor of 5. Okay, so again, just like this one, I want to stretch it and vertically shift it down by 3 units. Okay. And I want to write g of x, so I'm going to go with g of x, but now equals, in terms of f of x, means this thing is just going to use f of x to describe g. That's what in terms of. In terms of mean use this one to describe, in this case, g. So if it's stretched by a factor of 5, again, what I want to do is find the reciprocal of that number and multiply it by my input variable because I want to stretch horizontally and then vertically shift it downward 3 units. So if I'm going down 3 units, right, now I'm affecting the output. This whole thing now is my output. I want to affect that by going down vertically. So it's a vertical shift down. I need to just subtract 3, and that's all I need to do. So now let me just go back to example 21, go to Desmos real fast and verify that I did what I wanted to do. So it looks like what I wanted to graph was this sine function. So I'm going to come over here, get rid of all this, boom, get rid of it, get rid of it. And the sine function is just that. There you go. That's a sine function. Now I said that I want to stretch the heck out of this. So it looks like sort of like a little spring anyway. So, okay, I'm going to do this. So it looks a little, okay, no, a negative. So I want to see it a little clearer. There we go. All right, that's not too bad. There we go. So there it is. And now I'm going to come over here and just type in what I want to do, which is stretch it by a factor of 10. So I said that's only going to happen if I do this. And indeed, look at that. Look at that wave now. It looks like I took the spring and just stretched the heck out of it. Is it 10 times bigger? Hard to say. But it seems like that is the case. After all, what was one wave here? It's like a wave. So here's a position. Again, it's very hard to see. But it goes up, comes down. There's the other position. Where are these points at now? For example, this low point, where is it now? 1.6. Okay, if I take 1.6 and multiply that by 10, where am I? 16. Where's 16? Right here, looks like maybe. Yeah, I mean, this is 10, this is 20, this is 15 something. So yeah, it's about right. No, maybe right here. Yeah, more like here somewhere. Okay. So yeah, I think I have multiplied it or stretched it horizontally by a factor of 10.